Hello everyone, welcome to my talk. This is Sanhong from Alibaba. In my talk, I would like to share with you how we use OpenJDK at Alibaba. Here's agenda. Actually, I will go through 3 parts. The first part is how we use Java at Alibaba. I think the second part is a major part. We just share some experience how we customize OpenJDK for Alibaba business business needs. The third part is about how we build some internal tools for our diagnostic service to our Java developers. Before that, I just give you some brief introduction about Alibaba. Here is the Alibaba family tree. Actually, Alibaba is made of various companies. We are majorly focused on, you can say, online e-commerce market, computing platform, and financial, and as well as logistics platform. In Russia, I think most of you maybe are familiar with AliExpress, right? So actually, Alibaba has a local engineering team to do some support and build the entire distributed software stack to serve our AliExpress global customers. So, if you want to learn some more detail, okay. If you want to learn more technical details, I think you can go to Alibaba booth and get some more detailed information. Okay, let's take a close look at the Singles Day in China. Actually, Singles Day takes place on November 11 every year. On that day, many people just buy goods, gifts, or something like on Alibaba online platform. I think Singles Day almost the largest online shopping day in the world. This picture just focuses on our underlying IT support system used by Alibaba. You can just look at this picture. The red line is about our order service. We just got the peak number in last year. It's around 325,000 transactions per second. The blue line is related to our payment service. The peak number is around 256,000 transactions per second. So in my talk, I just focus on how we can optimize our software stack, especially from JVM perspective to support such huge transaction volume handling. Okay, this is overview. This is overview how Java has been used in Alibaba. The first thing is we customize our software based on very rich open source application. I just list on the right hand. You can see we already use HBase, Hadoop for our big data. We also use Tomcat and OSGI for our container. Also, we already run Java at a very massive scale. Actually, we already deploy millions of instances of JVM in our data center. The third keyword is about our service. Our architecture is service-oriented. It means we already create a lot of service. Each of service talked with each other by using RPC call. The last thing is our architecture is heterogeneous. Actually, for efficiency, many algorithms are written in C and C+ library. So C and C+ need to talk with Java by using GNI call. So this is our history, how we use OpenJDK. We started investment on OpenJDK back to 2011, since OpenJDK 6. And why we use OpenJDK? I just list the 3 important reasons here. The first reason is we get a chance to change OpenJDK code directly so that we can change it according to our business requirements. The second thing is we can handle some critical issue and no need waiting for official release. This is very critical for Alibaba business. The second thing is we just build some internal tools which can provide fast and better troubleshooting and diagnostic service for our Java developers. Before I go into technical discussion, I just list some key challenges we are facing. The first thing is you can see we have a very huge Java deployment inside Alibaba. So the key challenge here is how can we reduce hardware resource cost for such huge Java deployments. And the second challenge here is, I show you we need to deal with such huge transaction volume. For Java promise, we can Java just provides you infinite memory by garbage collector, and also Java gains native performance by using just-in-time compiler technology. But in another side, I think we are suffering from the longer stop word time of GC, and then because Java need additional CPU cycles to compile Java methods, so the compiler thread will compete for CPU cycles. Both of them will get worse and worse when the complexity of application gets increased. This is something we need to resolve. The third challenge here is, we have a lot of application, and then if we just use some tools shipped with OpenJDK, for example, JConsole or Visual VM, I think most of you are familiar with that. Actually, the first thing is we cannot use these tools to get enough finished information for our better tuning. The second thing is when we use these tools, for example, JConsole or Visual VM in our production environment, actually we just require the actual low overhead in our production environment. That's why we want to build our own tools for our diagnostic service. Okay, this is a high-level picture how we modify OpenJDK in Alibaba. In order to resolve those challenges I said earlier, we come out a couple of things here. The first thing is we call multi-tenant JVM. By using multi-tenant JVM, it allows to run multiple web applications into the same container safely. This is the first thing. The second thing is we just create we call the GCH technology. The full name is GCH. The full name is GC Invariable Heap. It's a free GC-free mechanism. You can manipulate objects as a normal Java objects, but we don't incur any GC overhead. The third thing is we just implement a coroutine in Java platform. We just use coroutine to avoid high thread context cost. So we also use implement Java-map. Java-map actually is very similar with Ready Now. I think Douglas already mentioned in the yesterday talk. And the last thing is we also build our internal tools. We call the Z-Profiler for profiling. Okay, let's go to the detail. How we can build our multi-tenant JVM technology based on OpenJDK. Let's look at the requirements. I think most of you are very familiar with this picture. We just did the comparison between traditional deployment and the multi-tenant deployment. If your application is run on top of Apache Tomcat, actually Apache Tomcat allows you to run multiple web applications into the same container. But the question here is, the Apache Tomcat does not provide solid resource consumption for each of them. For example, if you deploy multiple web applications into the same container, if somebody wants more CPU time than others, how can you just control the CPU time for each of them? How can you guarantee it does not have any impact on others? So that's why the key reason we come out of multi-tenant JVM technology. So inside the JVM, you can just look at the picture. We create multiple tenant resource containers inside the JVM. Actually, each of tenant resource container provides solid resource consumption control for each of Java module. Actually, you can deploy multiple Java modules into the same container. In runtime, these Java modules can map as, for example, as even a single thread or a group of threads. Let's take a close look at the tenant container API. What does it look like? We have a tenant configuration class, which is used to maintain resource consumption information for tenant. And also, we have a tenant container. This class is used to represent resource container for tenant. You can just look at this code example. You have a create of one tenant, and then you just specify how much CPU time and how much memory can be used for this tenant. In this example, we just specify 512 for CPU. Actually, CPU time is specified by an integer value. This integer value is a relative share of CPU time, which is available to tenant. We just use a very similar concept with control group. I will discuss it detail later. And the second thing is you just limit the maximum heap could be used by this tenant up to 512 gigabytes, right? So let's talk about the relationship between thread and the tenant. What's the relationship between them? You know, tenant container provides a run method. So when the thread enters to this run method, and then this thread will be attached to tenant automatically. After leaving from this run method, the thread will be detached from the tenant automatically. So all the code is running tenant container run method. And the second thing is any newly created thread inside the run method will be attached to the tenant or its parent thread. So let's come to a key question. How multi-tenant JVM do CPU management for tenant? We just implement our feature on Linux on x64 platform. So on Linux just provides control group functionality, right? So by using control group, it allows to your partition or process into a different group. And then you can set the different consumption policy for each of group so that you can limit the resource consumption for each of control group. So let's just put this concept into the JVM context. Back to hotspot JVM implementation. Hotspot just implement Java threads as a native threads. You can just look at this picture. You know, Java thread has an exact one-to-one mapping with native thread. In this example, we have a tenant container called tenant A, right? So tenant container A contains the two native threads. So for CPU management, we just put these two native threads into the same control group so that we can limit how much CPU time could be used by tenant, but by just relying on control group functionality. Let's take a detailed example here. You know, control group on Linux is represented by directory. In this example, for tenant 0, we just create a tenant 0 directory for tenant 0 tenant. In this tenant 0 directory, it contains a tasks subdirectory, right? So all the threads in tenant 0 will be put in this tasks subdirectory. Another important file is we call CPU.shares, which is used to configure how much CPU time could be used for this tenant. Actually, all the things are derived from control group. We just did some direct mapping from Java thread to native thread and then to control group. Okay, the second thing is how can we do tenant heap management for each of tenant? You can just look at this picture from bottom to upper, and our implementation is just is based on a G1 garbage collector. You know, from bottom, G1 GC just divides the entire heap into the equally sized heap region, and based on that, we just create what we call tenant allocation context. We call it tag. tag just helps tenant to manage a group of heap region. So you can say we just limit the heap. We just control heap consumption for tenant just by limiting the max number of the heap region that could be used by tenant. We have a very implicit principle here. One heap region only contains objects from a single tenant. That's the important reason why we need to do some related modification for object copy during GC. That we just need to guarantee the object must be copied into the correct tenant heap region. This is detail. As I have mentioned, our implementation is based on J1GC. So J1GC essentially is a copying collector. During GC, it just copy objects from space to space. So during GC, we just need to make sure we copy object into the correct tenant heap region. You can just look at this picture, tenant 1 and tenant B. So all live objects allocated by tenant 1 must be copied into the heap region owned by tenant 1 after GC. So we need to did the same logic to tenant 2. Actually, we have some other consideration for tenant isolation. The first thing is TLAB. TLAB is a fast allocation mechanisms. You know, TLAB is actually inlining. Is the space of TLAB is depend on heap region. As I have mentioned, the different tenant has a different group of heap region. You can just look at this picture. When thread A switch from tenant 1 to tenant B, we need to make sure it use the correct heap region for TLAB space. So we have two options here. Option 1, when thread A switch from tenant 1 to tenant 2, then we just retire the old one, and then recreate the new one in tenant 2. This option is relative to implement, but waste the space on TLAB. That's the problem. For option 2, it's a little complex. We just make TLAB as a tenant aware. It means we just maintain multiple TLAB buffers for the same thread. When this thread A switch from tenant 1 to tenant B, we just need to remap the TLAB buffers to use one which has been created in tenant 1. In tenant 2. The second change is for IHOP. As you know, IHOP is a threshold which is used to kick off concurrent market cycles. In original implementation, the IHOP is calculated based on entire heap, right? But in multi-tenant case, we need to recalculate IHOP based on tenant heap space instead of entire heap. Okay, let's take a look at what's the GCH. The full name of GCH is GC invariable heap. It means we create some hidden region inside entire heap. These regions are hidden from GC, so we don't touch it during GC. These hidden regions are managed by GCH tenant. Also, the key thing is we just provide some public API to our Java developers. You can just look at this example. The Java developers can use move-in API. They just move in your objects from Java standard heap to GCH heap region. The advantage here is, for Java developer, they can just manipulate these objects as a normal Java objects. They are very same with standard Java heap. And then we don't incur some additional GC overhead. This is the benefit we got. I think the important tips we got here is, if you want to get better GC performance, I think we need to define GC behavior according to your specific application logic. Here is a very high-level overview about the GCH. You can just look at this heap structure. We just allocate GCH heap region alongside the standard Java heap. Okay? Actually, you could have some reference from standard Java heap to GCH heap region. It's okay. But in operator side, it is illegal for you to have a reference from GCH to standard Java heap. Why we need to do this? You know, just to give you an example. For example, you have an object A, which is located in GCH. And the object A contains a reference to object B from the standard Java heap. The problem here is the object B might be moved by GC. So, as I have mentioned, we did nothing update to GCH. So when the object B has been moved by GC, so at this moment, the object A maybe contains an invalid reference to object B. That's a problem. So how to resolve it? We just support this, resolve this by using pre-existing pre-write berry. Pre-write berry has been explained in a previous talk. Actually, I just give an example. For example, if somebody wants to store some reference from standard Java heap to GCH, before storing, we just predict it, and the related exception will be shown and indicate the rule has been violated. So, where we are used the multi-tenant JVM? Actually, we are used multi-JVM technology for our Taobao personalization platform. We call it TPP. TPP is a recommendation system for our online shopping application. You know, for TPP just, they can deploy multiple microservices into the same container. So they just use multi-tenant JVM to limit the CPU and the heap for each of microservice. So where we use GCH? We are use GCH for our UMP platform. UMP is an e-commerce online application which is used for complex discounting calculation. And for our application, UMP application, the application owner just use GCH to pre-catch GCH data in local, so that they need not retrieve objects from remote cache server or remote database. As a result, we just save network bandwidth, right? And then we need not do any additional object serializing and deserializing work. So you can just look at this picture. We did a comparison between GCH technology and normal JDK. The blue line is about normal JDK. The red line is about GCH. We just can get almost more than 18% CPU saving by using GCH. The last slide is about, I know Belsoft from Russia looked into a similar problem, very similar with GCH. They just take another approach to reduce object deserializing and serializing cost. So I welcome Dimitri on stage to explain our post. Yeah.
Привет. Мы в Белсофте в рамках работы над OpenJDK открыты к исследованиям на тему того, какие, собственно, задачи стоят перед тем самыми деплойментами на миллионы инстансов и какие могут быть решения, применимые в рамках платформы. Санхонг рассказал нам только что, как в продакшене в Alibaba Java-девелоперы могут получить удобный доступ к off-heap данным, так как будто бы это был обычный Java-объект. Что интересно, да, это дает выигрыш производительности. Мы посмотрели, что произойдет со средствами, которые нам доступны в рамках OpenJDK. Оказывается, похожие вещи можно сделать при использовании функциональности, доступной в Project Panama. К примеру, если нам нужно использовать какой-то кусок off-heap данных как объект, мы можем это сделать, объявив для него layout. Например, при помощи специализированных аннотаций или даже в более простом виде, использовав C-header. И дополнительно мы можем использовать tool, который вы сейчас можете уже собрать, JDK Panama, который из этого C-хедера сделает то самое аннотированное представление. И, внимание, мы здесь видим код, который очень похож на то, что нам показал Санхong. Это Java-код, в IDE он замечательно работает, который в нативной памяти выделяет область данных и использует ее как Java-объект. Кому интересно, мы получили некоторые перформансные данные, какие-то сравнения. Мы это можем обсудить в дискуссионной зоне. Спасибо.
Okay, thanks, Dimitri. Thanks for your sharing your insights into Panama project. Let's go to Alibaba part again. Yeah, I just talk about how we can implement the coroutine in Java platform. Again, before that, let's talk about the reason why we need to do this. Actually, since Java was created, actually Java developer is very easy to create a multi-thread object, multi-thread application, right? So when you create many threads in your application, the problem here is, as I have mentioned, Hotspot or some other JVM already implement the Java threads as a native threads. So when you create many threads in your application, then you can maybe observe some high thread context switch cost. You can just look at example. I just give you a demo for this cost. For example, you have 4 IO threads, and then you create 200 business logic threads. And we just run this simple demo. You can see much more system CPU time has been consumed by thread context switch. It's very high. That's the strong motivation why we want to build a coroutine for Java. Actually, for our mechanism, we did 2 key things. In order to support coroutine for Java, the first thing is we need to add continuation primitive support to Alibaba JDK. Actually, this work is based on GKO patch. I'll discuss it detail later. The second key thing is you need to implement a user model. You need to implement a user model scheduler which is used to schedule continuation in the same thread. This is the key thing. The third thing is, for Alibaba has lots of legacy application. So our solution is very critical for our Java developers. So we need to make sure our solution is fully transparent to our Java developers. It means almost zero code change to our business application. It's very important for us. Our solution name we called WISP. This is the WISP explanation. Okay, the last important thing is our coroutine mechanism implementation has been widely used in Alibaba. We proved it does work for Java. Let's go to details. Before that, I just give you a demo example. How does it work? This is a very normal Java application, right? So you can just look at this code example. In step 1, you just create a normal thread pool, right? No different. And in step 2, you create another runnable task, which is used for accepting socket, and then you reading from the stream. In step 3, we create another runnable task, which is used to connect to above server, and then write out the data into the stream. It's a normal Java application. So how to do that? If you just run this application on normal JDK, generally, these 2 runnable tasks are run on top of 2 separate threads, right? But in our solution, it's totally different. I show you. You can just look at this thread dump. Firstly, in the same thread, actually we create 2 coroutines in this same thread instead of 2 threads. So the next thing is how can we make sure it does work? The key thing is we need to generate coroutine yield to events at all possibly blocking points. In this example, these blocking points include the first thing is a socket accept, right? The second thing is socket read. Then the third thing is socket connect. The last thing is socket write, right? So if we can generate these yield events at all these blocked points, so that we get a chance to, transfer controls between different coroutines in the same thread. It's a user model scheduler. So here is just a high-level summary for our goal or our approach. We just want to gain asynchronous performance by using coroutine, but meanwhile, we just want to allow our Java developers to write synchronous coding style. Because this synchronous coding style is relatively easy to implement and easy to maintain, also straightforward to debug. So this is our goal. Okay, let's talk about the first thing. How can we add continuation primitive support to Alibaba JDK? As I have said earlier, this work is based on multi-language VM project, actually from community. You can get that. Actually, we apply this patch into Alibaba JDK. We fixed a couple of bugs occurred in our production environment. You can just look at this picture on the right. In same Java thread, you can create multiple coroutines for this Java thread. And in details, we just create different stack for different coroutine. It means different coroutine will own different very separate stack. And the second thing is this patch provides a KAPI. It's called EL2. We can use EL2 to transfer controls between different coroutines. This is primitive support for our solution. So let's talk about the second thing, how you can implement a user model scheduler for coroutine. This is a key concept. We are relying on selector. By using selector, actually you can register multiple channels with the selector. And then when some I/O events happen, for example, socket read, socket write, socket connect, and socket accept, all of the things are listed as a selection key for selector. Well, when all these I/O events are completed, you will get notified automatically from selector. The key idea here is we just use the selector mechanism for coroutine scheduling for blocked I/O case. I just show you a detailed example. How does it work? You can just look at this normal application. On the top of the left, you write a socket application, and you have a synchronous read call, right? Client.read buffer. What will happen in the underline? You just can look at the code snippet in the bottom. This is our solution. We did two key things. The first thing is very simple. We just check whether or not the channel is readable or not. It's readable, then we get the results and return to caller. It's very simple. Otherwise, we did the second thing. This is the key. The first step is we just register this current read event with our scheduler, actually selector. And then we just can get a chance to yield to another available coroutine. It means we get a chance to schedule next available coroutine. Here's a high-level picture, how we do that. In this case, we have a thread, right? Then we create a scheduler for this thread. Thread and our coroutine scheduler has a one-to-one mapping. And then we use scheduler to manage multiple coroutines for this thread. So how to handle the blocked I/O case? Scheduler is fully relying on the selector to handle that. Because the scheduler will get notified when some IO events happened. When these IO events happened, then the schedule gets a chance to schedule next available coroutine. This is the key idea. So let's take a summary about our scheduling implementation. We called our coroutine scheduler as a Wisp engine. Actually, we already allocate scheduler Wisp engine for each of thread. And when for example, some coroutine is going to get blocked, we just reject some interesting events with the Wisp engine. These interesting events include, for example, socket read, write, connect. I have mentioned in previous slides. The second thing is some events related to thread parking. For example, you call a thread sleep with 100 milliseconds, right? Actually, in underlying, it will generate a thread parking event. At this moment, we need to reject this thread parking event with selector. So the next key question is when we schedule next available coroutine. Actually, I list two key conditions here. The first condition is when some interesting events happened. For example, some IO events are completed, right? It's very straightforward to understand. Or also some timeout events happened. For example, you call thread sleep with 200 milliseconds, and then that time has expired. So it's a proper time for scheduler to schedule a next available coroutine after 200 milliseconds. The second thing is some thread unpunking events. These thread unpunking events were generated by, for example, you call object notify or object notify all. The second condition is about when some user submits some new requests, then we need to create a new coroutine for serving this request. So then we need to schedule a new coroutine for this request. This is the second condition. Another interesting thing we already implemented here is we just implement what we call the Wisp thread executor. It's a normal executor service. You can just look at this code example. You just create a Wisp thread executor like a normal executor service. You can call execute, and then you can call submit for your runnable task. The difference here is all the submit runnable tasks are on top of coroutine instead of thread. This solution is fully transparent to our application implementer. They just can use our API for coroutine purpose. I think I go through the last complex part. How can we deal with synchronization for coroutine? It's very complex. I just saw a simple example here. In this example, we have coroutine A and coroutine B, A for full and B for bar. And in step 1, we just schedule test full in coroutine A. After that, in step 2, coroutine A just calls object wait, right? If we do nothing here, the current thread will be definitely blocked by the call on object wait. This problem. You can just look at this thread dump. If we do nothing, then we got a deadlock because the entire thread has been blocked here. We no chance to schedule next coroutine B. So how to handle that? Actually, Hotspot provides 3 kinds of log. The first log is fast log, right? So for fast log, the ownership of fast log is determined by address on stack. As I have said earlier, our coroutine has a separate stack. It means different coroutine will have a different stack. So for fast log, it's natural support. We do nothing here. And for bias log, in our current implementation, we don't support that. Actually, when we remove bias log, we don't see any performance downgrade in Alibaba production environment. That's okay for us. Let's talk about the complex case, inflated log. How to handle that? Let's check back to the example I showed you in previous slides. We also have coroutine A and coroutine B, A for full and B for bar. So again, in step 1, we just schedule and run coroutine A. And then after that, in step 2, the coroutine A calls object wait, right? After step 2, after calling on object wait, the current coroutine A will be put into the wait list. So after that, we did a different thing here. This is the case step in step 3. We just generate yield 2 event to main thread in step 3, so that we get a chance to run coroutine B in step 4 again. So when coroutine B continues, then it calls object notify. So the related unpack events will be generated. These unpack events will wake up coroutine A eventually. After leaving from execution of bar, then we have a chance to yield to coroutine A in step 6 and in step 7. So the deadlock I showed you in previous slides has been fully resolved by using this way. The case step is in step 3. We can generate yield event after call on object wait. Okay, let's talk about the performance number. When we use coroutine implementation solution for our carts application, carts is an online application for shopping carts. We just did some comparison between coroutine solution and the normal JDK. You can see we can got almost 10 CPU percentage saving for our situation. I think most of you may not have a chance to change the code, OpenJDK source code directly and add some such complex logic into OpenJDK. But the practice I would like to share with you here is if you observe high thread switch context cost, I think I suggest maybe you can try third-party coroutine library to boost your application performance. Okay, let's talk about the Java-map. Java-map actually is very similar with Ready Now, just presented in yesterday's talk, I remember. Let's talk about the warm-up issue. Warm-up is a very common issue for Java. You know, because Java need additional CPU because Java need additional CPU cycles for compiling Java methods to gain native performance. Actually, this problem during warm-up, actually, you know, they need the major problem here is the compiler thread will compete for CPU cycles during warm-up. That's the problem. Actually, during warm-up, we saw some problem. For example, because compiler thread compete for CPU cycles, so we got some timeout error issue. And also, we got some longer response time. Actually, this case will get worse and worse when the complexity of the application gets increased. For example, you load many measures class and compile many measures. Huh? Sorry. Okay, sorry. So in Alibaba, you can look at this number. It's very complex. That's why we need to do Java-map in our situation. Before Java-map, our application owner just usually use mock data to warm up JVM so that they can let JIT to pre-compile Java methods before real request come in. But by using this way, the problem here is the mock data is different from real data, right? So the mock data is not representative for compiler. That's the problem. So we saw some unexpected de-optimization case it dramatically hurts your application performance. That's why we come out with Java map. Java map is divided into two key steps. We call it record and compile. In Alibaba, we have two sets of environment. The first is we call it beta. The second environment we call it production. Both of them receive real user requests. And then the same version of application has deployed in a beta and a production. In beta, we just record necessary profiling data. And then in production environment, we just can pre-compile Java methods in advance based on some profiling data. Let's see details. How can we do some, which kind of information has been recorded in the first step? So we need to record which class has been initialized, which method has been compiled. Then we flash all of them to disk as a log file. In step 2, we just need to load the class eagerly and then initialize them eagerly. After that, we just ready to submit all things for compiler to compile them. Actually, the tricky thing here is how to handle class initialization. Actually, the complex here is, the order of class initialization is fully depend on the specific application logic. You can just look at the example. For example, the bar class initialization must be done after the execution of full test because it's using a full count, right? So how handle this? In our solution, we just do class initialization at the appropriate time after all necessary application logic has been executed. Okay, let's look at the performance number. Actually, we did a comparison between tier compilation, and I think you are familiar with the tier compilation, right? And the Java map. The X is about the time, the Y is about the CPU time. So in step 1, we just use Java map to pre-compile code in advance. So you can see, the red line is Java map, right? So after step 1, we just use a higher CPU than normal JDK because we just need to pre-compile this method in advance. And after step 2, when the real user request come in, and you can see the blue line and the red line, the blue line use a very high CPU than Java map. That's problem. But for Java map, after real request come in, we can use much less CPU during warm-up phase. It's quite portable. And after step 3, because at this moment, all hot methods has been compiled by tier compilation. So it's also use less CPU time. Actually, for Java map, we also have some other consideration. Actually, something already mentioned in the yesterday talk. The first thing is we cannot record any classes if these classes have been dynamically generated. They are from, for example, some GUI script. GUI script will generate some classes in runtime dynamically, or some classes generated by, for example, Java reflection or proxy. We just ignore them. And the second thing is we just need to disable some optimization. For example, not-check elimination. Why we do this? Because if we enable it, we just saw some unexpected de-optimization case. It's a problem. It hurts our application performance. Last thing is our current implementation does not be compatible with tier compilation. So if you want to use Java map, you need to disable tier compilation. Okay, let's go to the next, the last part. Let's talk about the internal tools we already built. You can just look at this picture. Inside the JVM, we have garbage collector, we have bytecode interpreter, we also have compiler, and in runtime, we have threads. And from memory perspective, actually, we have Java heap, we have metaspace, we have VM data, which has been used by VM internally. And we also have code cache for JIT. And we also have stack array for thread. So from our perspective, we just build much more profiling capacity based on OpenJDK. The first thing is you can say, we just modify garbage collector to add much more finest information. We just need to use this finest information for better GC performance tuning. This is the first thing. The second thing is for running threads, we just implement 2 key features. The first feature is called hot mess profiling. By using hot mess profiling, it can tell Java developers which method has used much more CPU. Actually, this is internal tools. If you want to profile your method, I suggest maybe you can try Honest Profiler. It's an open source tool, and it's more accurate for profiling. It takes a very similar mechanism with our hot mess profiling feature. The second feature is we call method tracing. We just instrument Java methods at the method enter and the method exit at the compile level. So we can tell the Java developers the wall time of method execution by using method tracing. And we also implement 2 key functionality. We just implement the dump functionality for metaspace and for code cache. So that, for example, if we dump code cache, we can tell our Java developers which class loader has consumed much more memory of code cache. Then they can check back their code and fix their problem. We also can dump metaspace. Then you can check whether or not your metaspace is fragmented, right? It's very useful for our Java development. Let's go through our internal tools. We call it ZProfiler. For ZProfiler, actually, we develop a JVM agent, which is running inside our JVM process on the left. And we also deploy create a ZProfiler server, which is a web server, and then it's implemented based on Apache Tomcat. The ZProfiler server has been deployed in our data center directly, so the ZProfiler server can talk with target JVM directly. The network is accessible. Also, our developers can use web UI to, ZProfiler provides 2 core functionalities. The first functionality is you can just simply click one button on web UI, then you can monitor the finest information of your target JVM. The second thing is it just provides some post-mortem diagnostics. I just give example. For example, if something goes wrong, and for example, in production environment, out of memory error occurred in your production environment, and for our Java developers, they just simply click one button, then the heap dump will be generated automatically, and that file will be downloaded from the profiler from the target JVM server to the profiler server. So the profiler web UI just show the full analysis results to the developer. So it's very efficient and high productivity. So you need not rely on some, for example, Eclipse MAT, right? So I just give a summary here. We have created multiple things to resolve the challenges we are facing. We have a multi-tenant JVM. We also have GCH, right? We have also implemented coroutine for Alibaba JDK. We implemented JVM. It's very similar with ready now, shipped with commercial Zen JVM. Also, we have our internal tools. We call the profiler. The last thing I want to mention here is actually we are happy to contribute our improvements based on OpenJDK to community. Actually, we have some ongoing discuss with community. For example, we just plan to contribute a Java map to OpenJDK. Also, we have some plan, participant in OpenJDK project. It's called Project Loom. It's a coroutine implementation for OpenJDK. Oh, okay, that's all. Thank you.